Thank you for coming back, and I'd like to continue the discussion. So in the first half in the morning, I gave a review of the local anomaly cancellation of superstring theories. We started from the spectrum, massless spectrum of superstring theories, and discussed the general theory of global and local anomalies, and explained how to compute the anomaly polynomials. We have seen explicit formulas for the anomaly polynomial and evaluated that in the particular case of type 1 and type 2 supergravities, and saw that in the case of type 2b, the anomaly polynomial is 0. And in the case of heterotic, we saw that the anomaly polynomial factorizes. So that's what we saw so far. Before going further, I'd like to make a philosophical comment. So what I find interesting about string theory is that not only it requires an understanding of various very general subjects, mathematical subjects like the theory of TQFT, invertible phases, etc., but somehow you need to apply that to a very specific choice of theories. So in this case of heterotic string, somehow you need to have a very specific combination of gravitino and a d-latino and the adjoint fermions, and not only just adjoint fermions for any Lie algebra, but you need to take SO32 and or E8 times E8. So because of this reason, superstring might not be a very good fit for mathematicians with who like general stuff, because at the end, I mean, after learning all these things, there are very specific instances where you can work on. But in those very specific instances, somehow things work so miraculously. And so I wanted to convey that feeling by actually doing the computation in front of you. So that's why I did that in front of you using Mathematica. I mean, you see, an hour ago when I showed this computation to you, everything worked so smoothly, right? Because I debugged the Mathematica code very carefully before doing that. But I mean, I wonder how Green and Schwartz did their computations by hand. They didn't have a good normalizations like we have now. So they used very weird normalization of various factors of 2 pi's to high powers with tons of strange rational numbers on top. But they found computations, I mean, their computation to give something sensible, right? And even with this Mathematica code, I had to debug it several times. And when finally things combine to have a very simple answer, that is something I feel very, special about it. So I wanted to convey that kind of feeling by showing this to you. So I wish some of you would try the Mathematica file, which I put on the web page, or you can try writing that code by yourself, for example, to see how special this cancellation is. So superstring theory is something you can appreciate if you like, for example, exceptional groups or sporadic finite simple group or something like that. It's something very special, exceptional, not very general, but requires a general understanding of various topics of mathematics. So that strange mix of genericity and concreteness is what I find most interesting about string theory. So anyway, let's go to the analysis of global anomaly. So let's start with the simple case of type 2b, I mean, simpler case of type 2b, where we found that the total anomaly polynomial is 0, right? So we want to show the anomaly theory total itself is trivial. So that you can consider the partition function of the 10-dimensional theory to be really a number, not an element in a one-dimensional vector space. How do we guarantee that? So this is a first step. What can we conclude with this condition? So we have an anomaly theory such that this is E 2 pi I L 0, which is 1, if MD plus 1 is a boundary of LD plus 2. So this is the condition we found so far on the anomaly theory. So what does it mean? So what this means is, what that means is the following. If you consider a more general situation where you have a Borodism between two D plus 1 dimensional manifold, this means that MD plus 1, this joint union, this orientation reversal of the other one, is a boundary of this D plus 2 dimensional manifold, which means that ZA is 1, but this is the product. And because the orientation reversal flips the it makes the partition function inverse, you get this. So meaning that if you have a Borodism between M and M prime, then this means that ZA of MD plus 1 is equal to ZA of MD plus 1 prime. This means that when the anomaly polynomial is 0, ZA determines a homomorphism from a Borodism group in D plus 1 dimensions to U1. And I intentionally made this part vague. So when we discuss Borodism groups, you need to specify exactly what type of space-time structure you put on the boundary manifold or the bulk manifold as a default choice. So if you have just spin fermions, you can consider something like this. So this is the Borodism group of D plus 1 dimensional manifold with just spin structure. When you have gauge field, it needs to be replaced by Borodism group of manifolds together with G bundles. So something like this, if you want to analyze E8 times E8 theory, and so on and so forth. In the case of type 2b, we just have metric and we don't have any other gauge fields. So let's say just consider metric plus spin structure. So what we need to study is just this group. So this is the group of 11-dimensional manifold, modulo Borodism in 12 dimensions. And this was computed long time ago by homotopy theorists, which turns out to be 0. So this is a trivial group. Therefore, once the anomaly polynomial is known to be 0, automatically, just because this group itself is 0, ZA is trivial. This means that all of the anomalies are gone, so complete cancellation. Great, you might say, but there is a catch. So this argument is applicable as long as we have a good enough understanding of all of the constituents of the massless type 2b spectrum. So for fermions, for chiral fermions, on the boundary, so you have N10, and you have chiral fermions. And corresponding bulk theory is a theory of infinitely massive fermions. Yeah? Then you can show that if you put a good boundary condition, you have massless chiral fermions on the boundary. So you have a natural bulk invertible phase, which plays the role of the anomaly theory for this boundary theory. So for chiral fermions, it's okay. And I thought that gravitinos are equally okay, but Kawahira-san just told me in the morning that he finds gravitino a bit problematic. So eventually somebody has to construct a good bulk theory for the gravitino to be perfectly happy about it, but presumably it can be done by considering a good theory of infinitely massive gravitinos in one higher dimensions. But I don't see any fundamental difficulty at this moment. I mean, you just have to come up with a nice Dirac operator acting on nice bundles and take the nice limit. But 5-form field is a bit different. So you have this self-dual 4-form field where F5 is something like DC4. So in this case, I haven't explained exactly what is the bulk theory. So we need to understand the combination of this bulk invertible phase plus the boundary self-dual theory so that we are sure that this bulk theory, bulk invertible theory, exists and has this field as the boundary degrees of freedom. And that bulk theory has to be defined on any 11-dimensional manifold. Only making sure that this is the case, you can apply this very abstract argument saying that because the voltage group is 0, the anomaly theory is 0. So the essential difficulty in type 2b global anomaly cancellation is not really about computing the global anomaly, but to make sure that you understand the self-dual field as a boundary mode over bulk theory. So that's the important part. So let's outline how it's done. So let me start with a 2D, 3D analog. So let's consider the Chern-Simons theory in 3 dimensions, whose action is something like ADA. And it is known that if you have a abelian-Chan-Simons theory ADA on a special two-dimensional slice of a finite extent with boundary, and let's say this is the time, then it is known that there's a chiral boson. And in this case, in 2D, there's a boson fermion correspondence. So this is the same as chiral fermion going around the boundary. So this is a very well-known system, even realized experimentally in the integer quantum Hall effect material. And what we aim to do is to generalize this construction when to the case when the boundary is 10-dimensional and the bulk is 11-dimensional, and instead of one form gauge field, you want to use 5-form gauge field. So at the level of fluctuations, analysis of the fluctuations, you can just repeat what people did, on what condensed matter physicists did in the case of abelian-Chan-Simons theory in 3D/2D in the 5-dimensional case, to show that if you have a, I cannot write any other figure. I mean, this looks exactly like this because I don't know how to write a 10-dimensional space. But if you have C5, DC5, and if you have a boundary, you can do a standard analysis and show that there are indeed chiral 5-form living on the boundary. So that's a very standard analysis. So the thing to be done is to make this thing precise. We need to make this thing precise. So that's the important thing. So before getting into this, let's discuss the Chan-Simons theory first. So I'm going to slowly start making coefficients precise. So the Chan-Simons theory, abelian Chan-Simons theory at level K has this exponentiated action where K is usually said to be an integer. So roughly, you start from this action and perform path integral over all of the one-form gauge field. So that's the idea. But you need to make sense of this expression. What is this? So you know exponential, you know 2 pi I, you know integral. And so it looks mostly okay. But the issue is this. So here, U1 connection, which I write as A, is not always differential form, globally well-defined differential form, right? So when the topology of the U1 bundle is trivial, you can take a trivialization and really identify A as the one form, then this makes sense. But in the other cases, it does not make sense. So what shall we do? That's the issue. And so you need to answer that question, and you need to extend that to higher form objects. So how do we proceed? So the way to proceed is as follows. First of all, we need to remind ourselves, or we need to learn what is a P-form gauge field after all. So let's say the gauge potential is Cp, and the field strength is of degree P plus 1, dCp, right? So U1 connection is an example where P is 1, right? So you have F2, which is dA, dA1. So you know this, right? You learn what the U1 connection is. There are cases when P is 2. So in that case, it's conventional in the physics literature to denote, use H for the field strength, and B for the gauge potential. And there are corresponding mathematical objects known for some decades. This is called a gerb, abelian gerb. Actually, we also know the P equals 0 case. In that case, you have, let's say, J1, which is d phi 0. So in that case, phi 0 is a circle valued scalar such that J1 is a 1 form. So this is a circle valued field, scalar field. So in the case of P equals 0, 1, and 2, there are nice geometric models of P-form fields, but this explicit description doesn't nicely generalize when P is more than 3. So that's unfortunate. There are many papers about the extension, but I'm not sure how useful it is. Instead, one possible solution is to use something called differential homology. So ordinary. So what is that? So we appeal to some physics intuition to motivate this, because I guess most of the audience members are from physics background. So what is this P-form fields? So we want to understand the set of P-form fields, right? Given a P-form field, you can characterize its topology by, say on manifold M, by taking its topological class, right? So in the case of U1 connection, its topology is the flux of the electromagnetic field, which is a degree 2 objects, and they are integer quantized and takes value in the integer cohomology of M. But when the topological class is 0, such P-form field is essentially a 1 form. So you have the space of 1 form over M, and there's a map from 1 form to the set of P-form fields. But of course, you need to identify a globally well-defined 1 form A1 with D chi 0. So you need to impose this kind of equivalence relation to get U1 connection. But this doesn't have to be, so this D chi doesn't have to come from a well-defined, globally well-defined function, chi 0. Chi 0 can be circle valued. So this means that this is quotiented by the subspace of the differential form, which is closed, such that any integral on a closed loop gives you integer. Sorry, sorry, so let's say we are talking about one form field, right? So in that case, this is H2. Chan class takes in H2. And in that case, the topologically trivial part is given by omega 1 modulo closed and integral periods differential form. So the space of one form field sits in this short exact sequence. So it has a quotient, which is the topological class, and the topologically trivial part is given by a differential form quotiented by closed and integral periods object. So differential cohomology does generalize this to arbitrary P. So you put P here, P plus 1, P, and P, and that's it. So this part is denoted by H check M or H hat M, depending on people. Because I need to use A hat genus, usually I use H check, but it's just a convention. And I forgot to write P plus 1. So I need to get used to it. I mean, it took a month or so to get used to this convention, but you need to, I mean, the degree of the differential cohomology class is the degree of the field strength rather than the gauge potential, but that's the thing. So that's one comment. Another comment is that there are many different definitions of the differential ordinary cohomology groups. It's analogous to the fact that definition of integer cohomology groups vary from people to people, like singular cohomology, check cohomology, blah, blah. But on nice manifold, all of the definitions give the same result. In the same way, there are multiple definitions, some of which is useful in one situation, the other of which is useful in another situation, but they all lead to the same object. So for now, let's forget about exactly how it is defined, but there's such thing. So we can try to say that P-form gauge field is an element of H check P plus 1. So let's see how far we can get. So we can get quite close, but not quite. So that's what we will find. So I need to explain to you some of the basic manipulations you can do in differential cohomology. So if you are given an element in HP and HQ, you can multiply them. So the good thing is that, so let's say element here is A, element here is B. Pardon? No, there's no degree shift. The important part is that everything is so you have a multiplication. This is graded commutative, as always. Yeah. I also get confused very easily. So let's denote by this the corresponding topological class, right? So these are the fluxes. These are the fluxes. In this case, you have what you expect. The product, you first take the product in the differential cohomology and take the flux. then it's just the product of the flux. So in other words, the product of differential cohomology lifts the product of the ordinary topological cohomology. That's one thing. Another good thing is that suppose you have a one form, sorry, p minus p plus, sorry, p minus one form, right? So let's say this is an element in p minus one m. Then you can regard it using this arrow as an element of the differential cohomology group. I mean, after all, differential cohomology is what mathematicians precisely formalize the concept of the p form field. I mean, p minus one form field in physics. So you can consider the corresponding element in H check P. So this different degree shift is what confuses us always. But let's say you have a p minus one and the b, say p q minus one in omega q minus one m, and so b check in H q of m. Then you can take the product A check B check, which in P plus Q, right? So this turns out to be related to in the following way. You just multiply A, D, B and take the check. So let's check that the degree match. So A has degree P minus one, B has degree Q minus one, and D has degree one. So in total, you have degree P plus Q minus one, which is exactly one minus P plus Q. So this differential cohomology product does for you what you want to do. So it multiplies the topological classes just as ordinary topological cohomology classes. And at the level of the differential form, it has this standard Chern-Simons coupling. So it looks very good. Hi. これですか? The question was how big this is. So this is just a space of topologically trivial one form field. I mean PP form field. So it's infinitely big. So this really is the space of P minus one form field. Not just topological data, but contains all of the smooth data associated to U1 connection and U1 gerb and higher forms. And one final very important fact about differential cohomology is that it has perfect A check, B check, so it's graded commutative. So A check, B check equals minus 1 to PQ, B check, A check. So this is the graded commutativity. Yes. So his question was how this can be consistent with BDA check up to the sign PQ, but this comes. So suppose further that P plus Q equals dimension of M plus one. So suppose this is the case, then fiber bundle, such that the fiber is oriented. And this gives an element in H check P minus dimension F of so that's what you know. And you apply this to this very stupid sequence. And you might think that this is only non-zero when P is equal to dim M, but that's not the case. Actually, so you have two ways of integration. So that's the funny thing. But it's kind of this is a gauge flux, and this is a gauge connection. Let's say you consider a very big. I don't write program. It's just so this gives just integral of Cp minus 1 over Mp minus 1. So this is so good thing about differential cohomology integration is that you can use the same differential cohomology. So let's say P plus Q is dimension M plus 1. let's denote this as A, B. So this is a pairing. So what we would roughly have written as FB
多分、音が、聞こえて、ズーム上の音声が半分くらい聞こえなくなってる感じだと思います。チャットでも。
Can you hear me?
Yes.
Sorry. The microphone died. Maybe 10 minutes ago. I'm sorry about that. Very unfortunate. Okay. So let me continue. So this is A check. But if you work out the coefficient carefully, this corresponds to, in the standard notation, A over 2 pi dA over 2 pi with coefficient 1. So if you use this thing as the action, this corresponds to level K being 2 in the abelian Chern-Simons theory. Not K equals 1. Why am I making fuss about K equals 2 versus K equals 1? This is because of the following. It's perfectly okay to consider Chern-Simons theory in 3 dimensions with arbitrary integer k. So this can be arbitrary integer on spin manifolds. As far as the Chern-Simons theory is concerned, but so this is on M3, and there's a Hilbert space of this Chern-Simons theory on two-dimensional manifold, right? So this is what we wanted, and for the application to anomalies, this needs to be one-dimensional, but this is one-dimensional only when k equals 1. So for any k, this action defines a TQFT in physicist sense, in that the Hilbert space is finite dimensional. But unless k is 1, this is not one-dimensional. Therefore, the boundary theory of chiral bosons or chiral fermions don't have partition functions rather than a partition vector. It only has partition vector. So you cannot use it in the analysis of the anomalies. I'd like to explain why very quickly. So let's analyze this action classically, right? So let's make a small variation. I mean, it doesn't have to be small because this is linear. So let's say you vary by this plus small a check. Then the variation is exponential 2 pi, something like twice a. And in the path integral, you sum over small a check. So this sets the delta function, which says 2a check is 0. And I mean, it's very tempting to divide by 2, but this takes values in h check 2, which is an abelian group, but there's no way to divide by 2 canonically. So this means that a takes values in 2 torsion points. Of H2. So what happens is that if you do the path integral of this boils down to a sum over 2 torsion points, which is still very non-trivial, and it will not be an invertible phase. Instead, path integral, so question was why I did this. I just wanted to derive equations of motion. Yeah. So one way to say it is to parameterize a check. Yeah. It's really standard way. I mean, you take the variation. So, but you vary this part and you also vary the other part. So you get twice the contribution from one single variation. Another way to say is this. So suppose you have 2-dimensional surface and P. You can pick a line, 1-dimensional submanifold X, and consider a differential, operator of this form. So let's say this is Ux. So this is the Wilson loop operator, right? As I said, this is just a fancy way of writing A. So this really is the Wilson line around here. And because twice hx is 0, this means that ux squared is 1. But you can show using standard analysis of Chan-Simon's theory. They do not always commute, but has this commutation relation where this is the intersection number. So, for example, if you have torus and the A cycle and the B cycle, if you start from this action, which you can write using differential cohomology product, UA, UB anti-commutes. So there's no way to realize such an anti-commuting unitaries on one-dimensional Hilbert space. Actually, the dimension is 2. And the same issue persists if you let P is 5, Q is 5, and dimension of P is 6, Q is 6, and dimension M to be 11. I mean, everything just goes through. It's really the same thing all over again. The only difference is that this is 10-dimensional. This is N10, and you can have S5 times S5, for example, instead of S1 times S1. So let's say this is A and B. Then this anti-commutation relation holds. So the boundary Hilbert space is not one-dimensional. It's two-dimensional. So you cannot use this as the action, bulk action, if you want to use it for the analysis of type 2B theory. So that's not possible. So the source of the problem is this 2, right? You want to get rid of this 2. How do we get rid of this 2? Where does this 2 came from? That came from the variation of this and that. So there, because you needed to vary this and that gave you an additional factor of 2. So if only we could put 1/2 here, we would solve the problem. So, but again, HX is an element in U1, so you cannot take a quarter of HX in a consistent way. You need a cleverer way. So what can be done is the following. So suppose, nonetheless, this object existed, right? It doesn't exist, but suppose it existed. Then it has a feature that it would have a feature that this is given by 2HX, B check plus HX, right? So this is the formula which would hold if 1/2 the differential cohomology product existed. So what you do is to just say that there would be a function QHX which satisfy the same equation. So the question was why we want this. And the reason is if we have this, you can use this for the small variation. So if you, instead of using capital V and small a, then you get this big HX, small HX with coefficient 1. This means that this is 0, right? So that's what you want. So instead, you assume that such a expression holds, and you call this Q the quadratic refinement. So it needs to be constructed. In 3D, it can be constructed for differential cohomology if you have a spin structure. You can construct in 7 dimension too if you have a spin structure. In 10 dimensions, you cannot actually construct it using differential cohomology, but please wait for 3 minutes. So what I explained so far is the following. I explained to you the concept of differential cohomology, which is a very nice mathematical way of precisely saying what the p-form field is. And it has a pairing generalizing making precise what the Chern-Simons coupling is. And it's very tempting to consider this, but it didn't work for our purposes. Instead, let's say we consider this action instead. So this is effectively 1/2 A check. So this should work, right? So one exercise you can do is to show this is invertible. Let me show it. It can be done very easily by using this characteristic feature of the quadratic refinement and also the Fourier transformation formula of the delta function in the space of differential cohomology. So let me proceed. So what you want to show is that this is always an element in U1. So that is enough to prove that this is an invertible theory. So what you have to show is that we want this to be 1, right? Let's show this. You just have the complex conjugate. Let's use B instead. 2 pi I Q B check. And because I took the complex conjugate, I became minus I, right? And I combine the integral, and this becomes exponential 2 pi I Q A check minus Q B check, right? Now I change the integration variable. So let's define A check to be B check plus C check. So it's a linear change of variable. So I change the integration variable from AB to C check, B check, right? Then the partition function squared, absolute value squared is just C check, B check, exponential 2 pi I, Q, C check plus B check minus Q, B check, right? Now you apply the quadratic refinement formula. So this is Q, C check plus Q, B check plus C check, B check pairing. Now this cancels. The only dependence on B is this C check, B check. As I explained, such an integral is a delta function. C check delta C check, which is exponential 2 pi I Q0, which is 1. So using quadratic refinement, you show that the theory is invertible. So all what is left for us to conclude the type 2B theory is globally anomaly free. You need to construct the quadratic refinement for the 5-form field. So So differential cohomology groups and the differential cohomology pairing have a general theory, but there's no way to construct quadratic refinement in general. It's an art. Yes. So for example, when P equals Q equals 2 and dim M is 3, one way to construct a quadratic refinement is as follows. You need to have, you are given an element, right, of H2, and you need to construct Q a check, which is roughly speaking 1/2 A2 pi d A2 pi when A is topologically trivial. And the way it is defined is the following. So I said that differential cohomology is a very nice uniform way of treating P-form field in general dimensions. But in order to define a quadratic refinement in this dimension, I need to go back to the original geometric understanding that this is a one-form connection. Right? Now, given M3 with a U1 bundle on top of it, U1 bundle, it is known that you can always find a null Baldism L4 together with a compatible U1 bundle, so such that this connection is also extended in the bulk. So here I used a lot of additional machinery to find a null Baldism together with U1 bundle. But once you do that, you can try to define this in terms of integral, not on M, but on L, f over 2 pi squared. And in this case, you can show that thanks to the special property of a spin manifold, if you have a spin manifold, you can show that this is always an integer. I mean, then so this is 1/4 of L4 C1 squared, where C1 is the first Chern class of the U1 bundle. So this is guaranteed to be integer, but still it's not guaranteed that we can divide by 2. But assuming further, L4 is spin, everything is spin, it is known that the intersection form in 4 dimensions is even. So this is actually inside 2z. So canonically, you can divide by 2 to get the integer. So this can be, so this means that QHX is now defined as a number in R over Z. So this is how quadratic refinement in dimension 3 is constructed. So as you see, I needed to use lots of additional materials. So we use the fact that in 3 dimensions, we have the vanishing statement that this is 0. So not just 3D manifold, but together with U1 bundle, the Baldism group is trivial. So that needs to be used to do this kind of analysis. Yes, this is spin Baldism. Thank you. So in 10D, nobody knows how to write down a quadratic refinement for the differential ordinary cohomology. I don't think it's proved that no such thing exists, but nobody knows. And furthermore, from various string theory analysis, it is expected from the start that the correct 5-form field to be used in string theory is not quantized by the ordinary cohomology. So string theory RR field the space of string theory RR field has a similar feature that topologically trivial part is given by, some gauge trivial part, but with P, M, where P is 3, 5, 7, type 2B. But it is kind of known beforehand that what should be here is not the integral cohomology group, but rather K group of M, K0 of M. So instead, what should be done instead is to use something called a differential K. For this purpose. And it so happens that for differential K, if you use a particular way of defining differential K using very particular cocycle construction, it is fairly straightforward to construct the quadratic refinement. Can be constructed just using spin structure. So the end result is that in order to formulate type 2B self-dual 4-form field with self-dual 5-form field strength, what you need to do is to start from the bulk 11-dimensional theory. So you have N10 and M11, and here you take an element omega check in differential K of degree 0, and you take a standard quadratic refinement, and you use this as the action. So this is the bulk field, and you can analyze this theory to your heart's content, and then you find that there's a 5-form field together with, F3, F7, which are related by Hodge star. So that's how it happens. So coming back all the way to the analysis of the global cancellation in type 2B, what we saw in the first half of the talk in the morning was that the sum of the anomaly polynomial of the Gravitino, Diratino, and the 5-form field is 0, right? And we said at the beginning of the afternoon session that as long as we can guarantee that the 5-form field appears as a boundary mode of some invertible field theory, then we are done, because the 11-dimensional Bordism group, spin Bordism group is trivial. And we just said that this is it. And that's it. So this concludes the analysis of the type 2B anomaly cancellation, including not just local part, but also the global part. So that's how it works. One comment is that, dozo. Sorry. This is the bulk 11D bulk field whose boundary modes are type 2B string theory RR field. So the degrees are shifted by 1. Yeah. So the question was why I suddenly had this sum, not just one particular degree of the differential form, but all of the sum. Is that, well, there's a general theory of differential cohomology for generalized cohomology theory. And so the general statement is that differential cohomology extends the topological cohomology by differential form where the coefficients are not just R, but R tensor the differential cohomology, original topological group evaluate at a point. So this is the part of the axiom of the differential cohomology, where the degree shift is that you have n and m, and n plus m should be p minus 1. So this is the general feature. So for ordinary cohomology, only non-trivial point cohomology group is for m equals 0. Therefore, you just have one term here. But for the K group, all of the K even point is there, right? So because of this gives you all of the differential form field separated by a degree 2. So that's what happens. Okay. So in the final 10 minutes, let me outline how it can be done, generalized to type 1 theories. Hi. Hi. Thank you for the question. So the question was the following. In the definition of this bulk theory, we have something in addition, not just the metric. So his question was, don't we have to consider the Bordism group, not just of metric plus spin structure, but metric, spin structure, and this field? That's a sensible question. The answer is this thing is actually integrated over. So it's not that this is introduced as an additional background field parameterizing. It's not part of the space-time structure in the definition of your quantum theory. It's summed over. So in the Bordism analysis, you don't have to consider. Yeah, you are using. That's right. That's right. Okay, so that might be also the source of the confusion. So there, in the degree 3 case, what I used was omega-3, sorry, 3 spin. U1 is 0. So this was to define extend from M3 to N4, all of the data associated. So this was to define quadratic refinement here. But when you define K-theory quadratic refinement, it's not necessary to extend everything into well-ordered dimension. You don't do it. Quadratic refinement here is basically just a gigantic eta invariant. So that trick is in the definition of the differential K-theory, and it's hard to explain in the remaining 10 minutes. But the idea is something like the following. Let me use the remaining minutes to explain the feeling of how you construct it, instead of going to the heterotic case, which is explained in the lecture notes anyway. So let me go back to the definition of ordinary cohomology, or ordinary differential cohomology. So this is the thing you want to do, right? So differential ordinary cohomology is like a combination of topological part and differential form part. One way to construct this is really just take integer cochain. So let's say you have an element omega here, and you take integer cochain. Also, you take some differential form of degree C minus 1, and you consider a pair, but that's too much. You take this data up to a boundary, and you take this data without dividing by this. So this is too much, right? And so what you want to do is to impose some equivalence relation between two such pairs. And differential cohomology can be defined in such a way. So it's fairly explicit, and in some sense, a very natural thing to do. I mean, you want to combine the differential form part and the topological part. So you just take a representative, combine in a nice way. So you want to do that also in the K-theory case. So you have ordinary K group and differential K and the differential form part. So K theory is given by taking a virtual bundle, virtual vector, complex vector bundle, E minus F over M, and take the equivalence classes. And so what you do is to take a formal sum of differential forms here, which is on this left-hand side. And on the right-hand side, you have this topological bundle. So one naive way to try to construct this differential K group is to consider the pair of such a formal sum of all the degree differential forms together with a virtual bundle, together with a connection on it. F, I shouldn't use connection A on it, right? So it's a huge amount of data, which is really too much. But the idea is to try to characterize the topological part by using an actual bundle together with a connection. And because that's not enough, you add the differential form part, and you introduce a gauge equivalence relation, which is basically saying that C, so let's just say this is A. So CA and C prime A prime are equivalent when C minus C prime is equal to the integral of dt of A hat Chan character F, where here in this computation, you consider the manifold M times the segment from 0 to 1, and you consider a family of connections such that A0 is A, A1 is A prime, but there's an interpolation, so you have a homotopy between the first connection and the second connection you have, and this you consider this as a connection on this bundle, and then you compute the Chan character and HX, you multiply by A roof genus, and you just integrate this homotopy direction. So this is the actual equivalence relation you put to get the differential K group. But long story short, in this particular definition of differential K theory, you have this bundle and connection. So when you define this QA check on M11, you just use this particular bundle and the connection and directly evaluate some eta invariant of the bundle constructed from this. And it takes some efforts to show that it actually is a quadratic refinement, but that can be done without extending M11 to N12. So you don't have to use this extension thing. So the good thing, one good thing about this K-theory approach of anomaly cancellation is that although you have to learn this heavy machinery of differential cohomology, you don't have to compute the Bordism group vanishing by horrible spectral sequence computation. So that's another comment. So in the remaining 3 minutes, I guess, let me reiterate what is going on in the heterotic case. I mean, type 1 SO32 case. So in this case, we already discussed Gravitino and the Diratino and Gaugino in SO32, right? And we saw that the anomaly polynomial, I mean, the sum of the anomaly polynomials kind of simplified, but still have some funny product structure. So it still wasn't quite zero. So what remains in type 1 theory is just on the boundary N10, and in the bulk M11, all you have is 3 form field and 7 form field, which are homogeneous to each other. So what you can try is to create these boundary modes by starting from the bulk action of this form C3D C7 plus ... So learning from that experience, it is known that in type 1 theory, the D-brane charge is, instead of K0, it's characterized by KO of M. So this is the space of the bulk fields. And you have a sum of differential forms. And because KO theory has non-zero cohomology, when degree is different by multiple of 4, it actually happens that the explicit cocycle representative of the differential KO is given by not complex bundles, but orthogonal bundles. And the connection on top of it. And then the formal sum of C3, C7, C11. So this is exactly what you want to have this bulk action. And then what you do is to look for the quadratic refinement to omega check for this quadratic, for the canonical pairing of KO theory. And using that, you can define a bulk theory for the boundary field of the type 1 theory. And you can compute the anomaly of this bulk 11-dimensional theory in a fairly easy way and show that its anomaly is exactly opposite of this. So you can cancel it. So that's how it works. The details in the lecture notes. But one thing I want to mention is the following. In this construction of the bulk field for the type 1 theory, I never mentioned supersymmetry. So all I said was that we want to have an invertible theory in the 11 dimensions, and we needed to choose some differential something. And I just said that, well, KO theory is a natural cohomology theory, so let's use differential KO. So if we say differential KO, and if we say let's use quadratic refinement, there's essentially a unique quadratic refinement. And you can use that as an action. I mean, even when you don't know string theory, right? If you are a fan of algebraic topology and differential algebraic topology, it's perfectly natural that you want eventually to consider quadratic refinement of KO, and you computed it in 11 dimensions, and you get some particular anomaly polynomial, right? That happens to be exactly the negative of the sum of the fermion anomalies in the type 1 theory. So that part is the miraculous part. When I started this afternoon session, I said that my interest in string theory lies in this strange intersection of the generic and the very specific, right? On this side, I'm just doing a very generic analysis of the quadratic refinement of some generalized differential cohomology theory. You do this in 11 dimensions, and somehow you get SO32, you get this particular combination, and every coefficient works out perfectly right. I don't know why that happens, but that's what it is. So thank you very much.
Thank you for the amazing talk and okay. But if there is some short comment okay.
Thank you. You can ask me in email or anything, and the lecture notes and the mathematical code is available on my webpage. So please send me corrections or comments. Thank you.
あ、すいません。ちょっと質問いいですか？
どうぞどうぞ。
すいません。ノンアーベリアンの場合の P フォームフィールドの数学的なモデルって今ありますか？できれば、アーベリアンの場合のスムースドリニコモロジー的な、こう、ローカルなディスクリプションを持つような。
So the question was, is there any model of non-abelian higher form field, right? So I thought that was the question.
そうです。はい。 Yeah, yes.
I don't know any, so that's my short answer. For ordinary U1 bundles, we definitely know the extension for non-abelian bundles. But today I used just abelian higher form fields. There have been many people and many attempts to construct non-abelian higher form fields, but I don't think there's any thing which satisfies me. So that's what I would say. Yeah, so please come up with something. That would be very great.
Thank you.
他に質問ありましたら。はい。
Okay, so there is no question as a comments. Okay. Okay, it's time to finish. Thank you very much. And the next lecture is the first start time is 3 p.m. right? Okay, 3 p.m. Thank you.